This section is the second half of the outline. I will cover more on theoretical percent yields down in here, but we want to look at calculations involving solution preparation, and solution phase reactions. Okay. Well, what is a solution? By definition, the classic definition is a homogeneous mixture. And its composition, it is consisting of two parts: a solute, the component in the smaller amount, and solvent, the component in the larger amount. Together, they constitute the solution, and I'll abbreviate it like that to save effort as we go along. Now, when describing a solution, it's typically done in terms of concentration. So what is concentration? By definition, it is an amount of solute in an amount of solution. When we talk about the amounts of solution as they apply to the idea of concentration, you can have weight-weight relationships. And typically that is expressed as percent composition, a weight volume ratios, and of course that is concentration terms in various terms, as in grams per milliliter, pounds per gallon, or moles per liter. It is the moles per liter that we want to focus our primary attentions on, and that has a connotation of molarity and is defined as a capital M, and by definition is moles of solute and divided by volume of solution expressed in liters. Now please make note of that denominator. It's not moles over solvent, is moles over the combination of solvent, which is the total solution. So solution preparation is really where we're going with all this. In general, it's dissolving a specified quantity of solute in solvent up to but not to exceed needed total volume. For example, you might have a solution designation of 0.15 molar. And what that essentially means is you have 0.15 mole of solute, whatever it is, dissolved in 1.00 liter of solution. And so in the interpretation of the concentration term, molarity is moles per liter. So given a black and white number, 0.15 molar, you should recognize that as the amount of solute in solution. And that solute, of course, is evenly and homogeneously distributed through the solvent. Now, out of the definition of molarity is being moles over volume expressed in liters. Solve this for moles. And of course that will give you molarity times volume in liters. And so this is what I specified earlier in solution phase reactions. So we'll be using both the molarity term and the molarity times volume relationship in solution reaction problems. Solutions are prepared from three specific sources. First, a manufactured solid stock. In other words, you order a sample that you're interested in or a reagent, and then they send it into a bottle and it's a solid reagent. I'll designate manufactured solid stock. Or a second source of solution prep, a solute for solution prep, is manufactured liquid stock. And the manufacturer will send you a bottle of liquid reagent we had a certain concentration. And third, a laboratory concentrate that you prepare. You are taking a quantity of concentrate and diluting it to a smaller concentration value for whatever experimental reason you would be working on. So that's the three sources. The main question is how much stock do you need? Well, in each one there's a simple formula, and I'll go through those each one, then we'll work problems that we have in the handouts and show you how this comes together. Okay, from solid stock, you're asking yourself, how much of the blue stuff do I need to pull out of the jar, put in the beaker, and add solvent on top of it? So essentially, you're calculating what mass in grams do you need to use or needed for your given solution. Well, that's a simple formula, and this one and the liquid will look identical except for one term: molarity times volume in liters times the formula weight of the solute, I'll itemize these in a second, over what we call a purity factor for that reagent. So the first one is solid stock, and this is your formula. Mass is molarity times volume in liters times formula weight over purity factor. M is the molarity needed, concentration. Okay, that's the, okay. V, of course, V sub L is volume needed in liters F weight, is the formula weight of the solute and PF is the purity factor. Some reagents in solid form come to you and they're not 100% pure reagent. Sodium hydroxide, for example, is about 95 to 98%. And so 2%, 5 to 2 to 5% is garbage. And so you have to take that into account and scale it up. Now this will be entered into the equation as a decimal fraction. And you'll see that, and it's not a big deal. Like that. So if it's a 98% pure, you want to divide by 0.98, which makes the overall number larger and takes out the impurities. The second source, second stock source, of course, is the liquid source. And the question there is, what volume of the liquid, say the sulfuric acid, would you need to transfer and dissolve to whatever volume you need? So we're talking about liquid stock. Incidentally, these are, I'm just repeating what's on this handout on the first page that I gave you. So you can follow me there if you wish on that handout, the solution preparation procedures. And then volume, and it comes out in milliliters needed of stock, whatever you're trying to extract and dilute, is molarity times volume in liters that you're trying to prepare. The formula weight of the solute divided by the purity factor, but it also contains divided by what is called a specific gravity of the reagent that you receive. What is the specific gravity? Well, if the solvent is in that reagent is water, then specific gravity is nothing more than the density of the manufactured solution that you receive. Hydrochloric acid is 1.14 grams per milliliter, and so that's the specific gravity as well as the density in the process. So you can get these off the assay label or out of a what they call an MSD sheet. An MSD is material safety data sheet, and manufacturers are required by law to send that MSD with any chemicals they mail out, and it is a complete description of that chemical and a number of factors. We'll look at that when we get into the lab. And how to use those to identify the chemical you're working with. So that's called a material safety data sheet. At any rate, the last one in this collection is what we call the dilution equation. And it's pretty straightforward in that it allows you to determine what volume of the concentrate do you need to pull from the lab stock concentrate and then add solvent to dilute to the whatever total volume you need, like that. Now there are a couple little problems in here. They have twists in them that I want to show you as we go along. If you are given a beaker that contains a quantity of solute, we're going to say so many 10 grams solute. And then we're going to add solvent. Let's see, in this solution, we're going to solvent to dilute it, the solute. And so we added some solvent. Now your solution level is this volume. And I've got a rather simple question here. Volume 1, diluted volume. Volume 2. You start with 10 grams over here and you poured solvent on it. How many grams of solute do you have on the one on the right? Do you have the same amount? Absolutely. That's the point I'm trying to make. You still have your 10 grams of solute in there. You also will have the same number of moles. Moles before equals moles after dilution. Moles before dilution equals moles after dilution. Because moles is a mass number. Moles is not molarity. Molarity is moles dissolved in a certain volume of solution. Is moles per liter. But moles is a mass number, like tons. Moles before is still moles after. Well, from the definition of molarity, which is moles over volume in liters, we can solve for moles, and that gives you molarity times volume expressed in liters. So I can take this molarity times volume and put it into that relationship, the equation equals, and I have molarity times volume in liters before dilution is equal to molarity times volume in liters after dilution. This is called the dilution equation. And it allows you to determine how much of the concentrate you need. You'll know what your concentration is on the shelf. You say you have a 5 molar HCl solution. Well, how much do you need to abstract and dilute to 200 mils, to make a 1 molar? Okay, so everything is known except one unknown. And we're fixing to work some problems that will use this idea. Problems in solution preparation, and I've got a couple of model problems here for each case that solution preps. Okay, we start out. Let's make a note. And we deal with moles and molarity. This is the first one. Okay, as you look at the set, how many moles of HCl are in 35 milliliters of 0.55 molar HCl solution? Okay, how many moles in 35 milliliters of 0.55 molar solution? What they're asking you for. Now, you're seeing again a combination of a volume term and a concentration term of a solution. Together, those constitute what we call solution data. And when you can take solution data and convert to moles by multiplying the two together, but the volume has to be in liters. So moles is equal to molarity times volume in liters, and so molarity is 0.55 molar times the volume in liters, which is 0.035 liters. Now molarity, I can expand this just for instructional purposes. Molarity is moles over liters. That's the definition of molarity. Moles over liters times 0.035 0.035 liters. Liters cancel, and we're left with moles, and so that would be 0.55 times 0.035. And so we have 0.019 mole of solute. Okay, that's the simplicity of that idea. Now, it will, when you are working reaction problems in solution, you'll have, say, 35 milliliters of 0.55 molar HCl reacting with 25 milliliters of 0.75 molar, and you've got to convert those to moles and see how they relate to the equation. And once you get the product generated, then you convert that back to a concentration term. We'll work through that here shortly and show you how that takes place. Okay, so that's the number one in our model problems. Okay. If 0.15 moles of sodium chloride are in 125 milliliters of aqueous solution, what's the molarity? So you have your solution is 0.15 mole of NaCl and 125 milliliter solution. What's the molarity? Well, you simply apply the definition of moles over volume, but that volume must be in liters, as we emphasized here. Moles is 0.15 mole over 0.125 liters, and moles per liter, of course, will give you the molarity you need. That was already 0.021 molar. Okay. Yeah, make that correction. I'll correct that when I get home. All right. Number 3, what volume of 0.22 molar sodium hydroxide will contain 2.5 moles of sodium hydroxide base? Okay, so this is the application where you solve the definition of molarity for volume. Solve the definition of molarity for volume. So molarity equals moles over volume expressed in liters. So it's asking for volume, which is molarity times moles over molarity. Sorry. So the volume, now this will come out in liters. So we have 2.5 moles of the sodium hydroxide, and we have a point molar solution. That's moles per liter, so it's going to come out in the volume in liters. So that's 2.5 divided by 0.22, 11.36 liters on that one. So I think that one checks out. Okay, what's the molarity of a solution prepared by dissolving 23.45 grams of sodium bromide salt in water to give 150 milliliters solution that gives you the formula weight? The solution is, what is the molarity if you have 23.45 grams in 150 milliliter solution? Well, you need to go to moles on the top, and you need to go to liters here. That's the long and the short of that. So to get to moles is 23.45 over grams, grams, I'll string it out. And is it 81 grams per mole given there's your numerator, and it's 0.150 liters. And so working through that, we make sure we got it, look like 1.93 it says. 23.45 divided by 81 equals divided by 0.15. And so that's a 1.93 molar solution in the sodium bromide. So as amount in a volume of solution, and you convert it to moles per liter. Okay. What's the molarity of an aqueous solution if 0.2074 grams of KHPH, and that's potassium hydrogen phthalate. That's a standard for calibrating hydroxide bases, and we'll use that in lab next time. So that's given 0.2074 grams of KHPH in 100 milliliters solution. What's the molarity? Well, this is the same as the previous. You just got to convert the mass of KHPH to moles. This gives you the formula weight is 204.22 grams per mole for, I think it's done it, yeah. And so the molarity M of the KHPH solution is 0.2074 grams divided by 204.22 grams per mole, and that's divided by 0.100 liters. And so that's the long and the short of that.
If he says 0.1, then I'm converted.
You get a 0.01 or 0.1. Let's see, 0.2074, 204.22 divided by 0.1. I got a 0.01. 1 molar. And I don't know where I'm getting some of these numbers. I just jotted these down offline. I had to make that, based on that, should be 0.01. Okay. Okay. It's asking how many grams of KClO3 would be needed to prepare 250 milliliters of 2.25 molar aqueous solution, and it's giving you a formula weight and a purity factor there. Okay. Prep 250 milliliters of 2.25 molar potassium chlorate. The solution, formula weight, KClO3 is 122.56 grams per mole, and purity factor is 1.00, 100%. Like that. So really what we're doing here is, well, we've got a solid reagent, KClO3, on the shelf, and we need to know how many grams of that would we need to put in the container, dilute up to 250 mils. And so grams, how many grams of KClO3 is molarity times volume in liters times formula weight, just the formula I gave you, divided by decimal fraction, which is 1 in this case. So we're trying to make a 2.25 molar solution, that's moles per liter, and 0.250 liters, because that's converted to liters. And formula weight is 122.56 grams per mole, all divided by 1. Now that's moles per liter, so liters drop out, and we're left with moles there. Moles drop out here, and so the only unit left would be in grams. So we have 68.94 if you check that. So you would need to transfer 68.94 grams of the KClO3 into a mixing container and add solvent up to, but not to exceed, the 250 total volume out of that process. But the thing you need to learn is that formula. It applies to all solid source samples. Okay, what you're given is a solution of sodium acetate in which you are mixing 135 grams of an impure salt into 225 milliliters of solution. The salt is 96.2% by weight. How many grams of pure salt is mixed into the solution? Okay, so you are mixing 135 grams of 96.2% sodium acetate. That's an abbreviation. NaOAC is sodium acetate, shorthand, into 225 milliliter solution. How many, and it just simply wants to know how many grams of pure stuff you have. Well, actually, it's 96.2% of the 135. That's all you need to do. So, grams of NaOAC equals 96.2% of 135 grams, or 0.962 times 135 grams, or 130 grams of pure NaOAC. So it reads a little more complex than it is. Now you can actually calculate that number from that molarity volume formula weight, purity factor equals mass added. But I think that's a long way around that. So I would strongly recommend the shortcut here. Okay. And finally in this set, what volume of lithium hydroxide would contain 63 grams of lithium hydroxide, pure stuff, having a molarity of 1.55 molar. So this is applying the gram formula in solving for volume. So grams needed is equal to molarity times volume in liters times formula weight over a purity factor. And so it's getting 100% pure. So we got 63.2 grams given, and the molarity is 1.55 molar. The unknown is volume, is going to come out in liters. The formula weight is given 2395 grams per mole, and it is divided by 100%, 1.00 purity factor. And so here's your equation on one unknown. So the volume in liters is 63.2 times 1 divided by 1.55 and 23.95, and it's all coming out in liters when you punch that in. So it's just a twist on the same problems. It's just, well, you can calculate different things, and you can expect different parts of the equation to be in the question problem question part, 1.68 liters. Like that, okay. Moving right along. Okay, now, as you recall, this is a question where you're asking what volume of the reagent do I need to put in the container and dilute. Well, you want to be cautious here with strong concentrated acids. If you have a strong concentrated acid, remember A and W root beer. Add acid into water, then dilute. You might say concentrated. So I emphasize this for safety reasons, as you can tell from the notation. The process of mixing the solution is pretty straightforward. You're just diluting the solute. But if you are in a practical environment, you certainly want to exercise caution if you have concentrated acids. Okay, so that is really number one in the problem set right there. And a typical here, you're given 37% solution of hydrochloric acid in aqueous medium. What volume would you need to prepare 100 milliliters of 3 molar solution? And you're given a specific gravity, 1.14, and that's a density, grams per milliliter. Now, purity factor is 37%, or 0.37 that you put into the equation. As when you look on the assay label on the bottle, it'll say HCl 37%, or nitric acid 47%, or sulfuric 98%. And so that's what you use in the equation. Let's see what else they give us in that. Oh, of course, the formula weight of HCl. So volume in milliliters needed is, again, molarity times volume in liters that you're making, formula weight, purity factor, divided by specific gravity. So you're trying to make a, what are they asking for? 3 molar. Yeah. So you got 3 mole per liter solution you're trying to make. You're trying to make 100 milliliters, which is 100 liters. Formula weight is 36 grams per mole. Purity factor is 0.37. Specific gravity is 1.14 grams per milliliter. Well, grams drop out, moles drop out, liters drop out, and we're only left with milliliters. And so you extract that much and transfer into a small quantity of water and then dilute up to, but not to exceed 100 total milliliters. And so whatever that is, knock it out. 25.6. 25.6 milliliters of concentrated HCl into, say, 50 milliliters solvent water. Mix, and then dilute to 100 milliliters total volume. So that kind of gives you a kind of a cross-section, thumbnail of the mixing procedure right here. It says if 50 milliliters of concentrated nitric acid is used to prepare 2 liters of 5 molar aqueous solution, what's the molarity of the manufactured stock? The simplest way to do these is you can go around in circles with one of these, but it's a 68% nitric acid solution. So that's really what they're asking. What's the molarity? And they give you specific gravity is 1.42, and that's density of the manufactured solution. And I'll give you the formula weight or anything. Let's see the formula weight of HNO3. 63 grams per mole is the formula weight of nitric acid. I don't think we need anything else. You don't need all this other data in there to calculate that concentration of the manufactured stock. What does this mean in terms of 68%? Well, it's a weight-weight ratio. 68% HNO3 simply means that it's 68 grams of HNO3 per 100 grams of solution. Now convert that to moles per liter, and that's your stock concentration. So in this case, 68 grams of HNO3, I just put grams, divided by 63 grams per mole will get us numerator definition of molarity. That'll get the numerator to moles, and the denominator is 100 grams, and you've got to divide that by 1.42 grams per mil to get it to milliliters, and then all of that divided by 1,000, so that's got to be multiplied by 1,000 milliliters per liter, like that. And so that's 68 divided by 63, that's 1.08, and that's divided by 100 about 1.207. That's what I got, and that's going to come out in moles per liter, and so that times 1.08, and that's about a 15.3 molar manufactured stock HNO3. So that's quite concentrated, and yeah, is very dangerous if you're not careful to watch what you're doing.
Can you adjust the key on that one also?
Okay, what volume of water? Now, this is a tricky little question because you've got to stop, concentrate, and you're asking first, how much do I need to pull out of that? Well, that's what you start with, a volume you start with, then you got to add water, and that's what they're asking for. How much water do you pour on what you extract? And let me show you what the deal is here in this first one. What volume of water must be added to 30 milliliters given a 30 milliliters of 5 molar calcium chloride solution? Okay, and you need to dilute to 1.0 molar. How much water to add? Okay, now using the dilution equation, the volume that you determine is the volume you must use and then dilute. Okay, so molarity times volume before dilution equals molarity times volume after dilution. So before dilution, your question is, how much of this do I need to extract? And I'm diluting a 5 molar sample. So that's 5 molar times whatever the volume is equal to, you're trying to make a 1 molar solution. How much water do you pour on to make a 1 molar solution? Is that all they give you?
I'll give you 30 milliliters.
What volume of water added to? Oh, to get it down to 1 molar solution. Oh, you started with 30 milliliters. Yeah, okay. That's your final volume. Okay, so you have your 30 mill. You don't have to change the units here because both sides will be the same. And you can work, but it's 6 on one side, half dozen on the other. What this gives you is the final volume. So if you get the final volume is 5 mole per liter times, well, cancel this out, 0.03 liters if you moles over 1 mole per liter. Moles drop out. You've got liters here, so that gives you your final volume in liters, and so that's 5 times 0.03, and so that's 0.15 liter, which is 150 milliliters. But you started with 30 milliliters. That's what it said. You started with 30 milliliters up here. So if you subtract that, you have 120 milliliters of water added on top of the 5 molar calcium chloride solution. And the results is whatever you're trying to make. So you're adding that 120 mils on top. So that's kind of a twisty problem. Usually you're just trying to, well, how much of the concentrate do I need? And you've already decided on what you're trying to make. Let's see what this next one is. Okay, what's the concentration after mixing? Okay, let's see what this second one we can get out of this. You say you're given 60 milliliters added to 80 milliliters of 2.50 molar hydrochloric acid. Okay, what's the concentration of the HCl solution after mixing? Well, if you're pouring 60 milliliters of water on top of 80, you'll have 140 total volume. is 60 plus 80 mils. That's 140 milliliters final volume. So applying the molarity times volume of before to molarity times volume after, what you have is the molarity before. You got 2.5 molar. The volume is 80 mils before, and that's equal to an unknown molarity after times the total volume, because 60 plus 80 is 140. Solve for the molarity after, and that's 2.5 molar times 80 milliliters, all divided by 140. Milliliters drop out, and you're left with the final concentration. And it's 1.43, I guess. So, anyway, those are just models of the types of problems you'll see next week, and it'll be just as straightforward. Or, let's see.